Kia ora. In this brief video, I'll describe some of the main findings from our recent study. Prolonged cycling reduces power output at the moderate to heavy intensity transition, which was just published in the European Journal of Applied Physiology. The study was led by our master's student, Julian Stevenson. So as applied exercise physiologists, we routinely profile the physiology of endurance athletes for purposes of assessing performance capability, regulating training intensity, and to help with programming of training, and also to allow the monitoring of training load. Now, like in many labs, the primary approach that we take in order to do this is using an incremental exercise test. So we take a series of different physiological measurements at progressively increasing work rates. We use gas exchange to derive movement economy, substrate utilization, and also the peak rate of oxygen consumption, or VO₂ peak. And we use gas exchange and blood lactate measurements in order to derive physiological thresholds, or the boundaries between the different intensity domains. So these intensity domain transitions are particularly useful for the programming of training, the regulating of training intensity, and the monitoring of training load. Now, an issue that we face in this physiological profiling space is that the data collected and the estimates generated in the course of a 20 or 30-minute assessment is used to guide and monitor training sessions that may last several hours. So as our exercise physiology is not static over time during prolonged exercise, we recently proposed that an athlete's three-dimensional physiological profile, that is, the relationship between their physiology, the exercise intensity, and also the exercise duration should be considered, which we summarized in an article on this so-called durability concept. So we define durability as the time of onset and the magnitude of deterioration in the different physiological profiling characteristics over time during prolonged exercise. Now, some of the key studies that already exist in this field were led by Ida Clark and colleagues. So they performed a series of studies using the 3-minute all-out test, and they determined that the power output at the heavy to severe intensity transition decreases following prolonged heavy intensity exercise, with the precise mechanism behind that unclear. So the heavy to severe intensity transition decreased with prolonged exercise. Now, in the study that I'm talking about now, we followed this up. We recruited 14 well-trained cyclists to our lab for a straightforward 2-visit study. So they performed a traditional profiling assessment in the first visit, and in visit 2, they undertook a targeted 5-step incremental test, and they did that before and after 2 hours of cycling at 90% of the previously estimated VT1 power output. So in these 5-step tests, we used expired gas analysis and also measurements of blood lactate concentration to estimate the moderate to heavy intensity transition using both the first ventilatory threshold, or VT1 method, and the log-log lactate threshold method. Now, perhaps unsurprisingly, based on the data that was already there on the heavy to severe intensity transition, we found that power output at the moderate to heavy intensity transition, and whether that was defined by VT1 or log-log LT, we found that declined following the prolonged exercise. So this was consistent across the participants in the cohort, with the average reduction in power output being about 10%. So these results, and also those of our other outcome measures, were inferentially identical between the VT1 and log-log LT parameters. So from here on, I will only refer to VT1. Now, given that power output at the transition decreased, as you would expect, we also observed a reduction in the rate of oxygen consumption, or VO2, and also the rate of whole body energy expenditure that was associated with the moderate to heavy intensity transition following prolonged exercise. So there was a reduction in VO2 and energy expenditure at the point at which the athletes transitioned from moderate to heavy intensity exercise following prolonged exercise. Now, we used regressions of both the pre and post prolonged exercise energy expenditure versus power output relationships to determine the contributions made by a reduced efficiency. So that's the reduced conversion of metabolic energy expenditure into mechanical power output on the bike, as well as reduced achieved rates of metabolic energy expenditure at the transition, which is what we observed on the previous slide. So we looked at the contributions made by both of those to the reduction in power output that we saw at the moderate to heavy intensity transition. Now, as shown here, we found that both made meaningful contributions, and the magnitude of these contributions was not different. Now, lastly, we also measured the heart rate associated with the transition before and after prolonged exercise, and we found that the heart rate associated with the new lowered power output at the moderate to heavy intensity transition, that increased following prolonged exercise. So if your VT1 occurred at 220 watts and 150 beats per minute initially, it may have been more like 200 watts and 160 beats per minute after the prolonged exercise. So this demonstrated that the classic cardiovascular drift that occurred during the prolonged exercise, the decoupling between heart rate and power output, that was proportionally greater than the downward drift in the moderate to heavy intensity domain transition. So this, I think, has implications for the programming and within session intensity regulation when using heart rate. Thanks for watching. I hope you found this summary video useful.